I was at ISI since 2004. So from 2004 to 2011, I started as a research assistant when I was doing my master's degree at USC Computer Science, and then I was a research programmer. I came back to do my PhD with Craig Knobloch, and I stayed for a postdoc position for another 3 years. So that's pretty much everything at ISI. At ISI, one thing that's very interesting is not only we work on fundamental research in computer science and other disciplines, we also build useful systems because like DARPA project, we need to be able to show our result, we need to be able to demonstrate a working system, and that naturally leads to startup. Because once you have people who are interested in your prototype, we want to be able to make the prototype better, eventually become a product. When I was a master's student, we worked on a project to integrate geospatial data sets from different sources. And this can be road vector data, road lines, road geometries, and this can be point data about locations. This can be satellite imagery, this can be text. So the startup is based on a pattern. Craig and I and another PhD student, Jason, and also Cyrus Shahabi in the department. We all work together on this pattern, and then Craig and Cyrus had this startup, work at the startup. We look at different types of data and how do we integrate all this spatial data to help us more understand what's going on Earth. We started this company based on a pattern on data integration. So the technology is to look at different types of spatial data, integrate them so that we will be able to better understand what's going on Earth. So for example, in a city at a certain location and collect it from different sources. One of our customers is looking for people who own a house and has a pool because they are doing pool supplies, and they want to be able to figure out the addresses of these households. So we take road data with addresses, we take satellite imagery, use satellite imagery to figure out houses, pool, use road vector data to figure out addresses. We combine them together, generated an integrated data set that tells people many interesting things. My work always contain a real problem. To solve a real problem. Like we do air quality prediction and forecasting. And the challenge there is you only have limited sensor. For example, Los Angeles, you only have 200 sensors. What about the people living in the location that they do not have a sensor? How do they know the air quality in those regions? So what we are building, or I am building in our lab, is algorithms that can take all kinds of data and to solve critical problems that can benefit people. People say, oh, now we can have this fine-scale air quality prediction. We can start to understand people's exposure to air quality. If you take the buses to work, this is your route. This is your air quality. This is your exposure to air pollutant. And without machine learning tools, you cannot really do that. Right now, because all the tools are very easy to use, when I say tools, it could be software tools or systems, right? Database systems, machine learning libraries. So people, when we teach students how to use all these tools, we teach them about the algorithms, about the computer systems. But I think one thing that's very important is to understand the bias in the data set and also the bias in the algorithm. And I would say that's a very important component. For example, if we train the model with thousands, millions of faces to do face recognition, it can work very well. But does the model has a bias focusing on certain type of people? Does training data has a bias? And how do we know? And if there is a bias, what should we do? I think that's a very important component that many universities are starting to address in this topic in courses, but still not enough. I'm an associate professor, computer science and engineering in the University of Minnesota. So what I'm working on right now is spatial computing in the area of spatial AI. So we build machine learning algorithms to handle spatial data. For example, we look at how we can build machine learning algorithms to automatically read historical map scans. Like for example, in the US, we have thousands of historical maps that covers the entire 125 years in the past. And you cannot really get any detailed information like this from other sources. These are pre-satellite. So if you want to understand how highway change how people live in a city, historical map is your answer. But there are only in the paper format or image format. To understand them, we need to use the machine to help us extract information from them and integrate with other data set. So one example would be when people want to understand how urban development was happening in the last 100 years, they will be the users of the historical maps. Because historical maps tell you how the road network grows over time, how people's building from how people build physical infrastructures from one place to another place. Also, historians, they like to look at what are the names or place tags happened on the map. How did people make the decision to label some location but not other locations? Right? So those are very interesting questions that need historical maps to answer. We have been looking at collections of observations. So for example, people would say, hey, I saw a specific type of bird in this area. And that helps us to understand where are these species, where were these species, maybe 100 years ago, 50 years ago. So these are long-term collections of observations. But one thing that's very interesting is in LA, there was a record. They say, oh, we found this species near a place called Mesmer. But if you go on Google Maps, you cannot find Mesmer. It's not a neighborhood, it's not a place name, it's not anything. So we went on to look at historical maps. It actually is there. So Mesmer is a neighborhood near Playa del Rey. It turns out some developer was actually want to build a neighborhood called Mesmer, but it eventually didn't work out. But the name kept on historical map, but not anywhere else. They started with paper maps, and libraries, museums, they start to scan these maps into images. But you don't have any metadata, so you cannot find them. So when I was at USC, every time when we need a map, we talk to the digital library people, and our librarians will go to the warehouse and help us find those maps in paper format and scan them. And that's not going to scale, not going to help us find interesting maps. So one way we are working on this is we build a generic machine learning tool that are able to read these maps, find text on these maps, and link this text to existing data set like Wikipedia, OpenStreetMaps, so that we know, hey, this name in the contemporary data set was mentioned in certain maps. So this helps us to create some index so the user can start to search for these maps. For example, search for all historical maps in California covers a mountain peak over 100 meters. So that's the first step. Now, once we can find these maps, the machine learning tools start to look at different types of geographic features like roads, wetland symbols, railroads, and convert them to a format that we can analyze. And like traditionally, this is a supervised machine learning approach. That means the machine needs to have lots of training data. But since maps are spatial data, if we start to have maps at the same location over multiple years, we know the things in this map will not change much, and the change will be gradually. So we can use that as a hint to train the machine learning model so that we don't really require that much training data for recognizing features on the historical maps. Linear features will be railroads, road lines, symbols will be like wetland area, buildings, important infrastructure like abandoned well. In California, there's lots of wells, old wells, but we don't have any records of them. Those are potential pollution sites. And when government want to spend money on recovering those sites, we need to first know where they are. There's no other information but historical maps. The same for railroads as well. When we were looking for places to buy a house, I look at all the historical maps of a certain area to see what are the contamination sites in that area, because railroads is a really big pollution sites in history, and you don't really know where are all these old railroads. So for general public, just by looking at maps, I think it's really fun. You want to look at maps that where you grow up, where you currently live, where you want to move to, but you have to find these maps, right? So our technique will be able to enable that. And now once people start to look at these maps, they can help also contribute to digitize this map, and then we can start to build a 3D world of the past. We work with Google AI on this topic for Manhattan area as well. We look at how we can use New York Public Library maps and current map data, and also historical photos. So from the map, you have 3D, you have two-dimensional building outlines. From the photo, you have the building facade and you have the 3D model. So put these two together, we can build a VR world. People can walk in and look at 1920 Manhattan. What we are working on right now is to connect our machine learning tool with different types of community users. We call them community users because for librarians, they're looking at these maps, they want to quickly generate metadata so their user can find these maps. For historians, they want to be able to quickly convert these maps into digital format so that they can use the data and do interesting studies. What are the names in the map, where they were, and what we call such things in history. So what we are working on right now is we are integrating these machine learning tools with a web user interface. So the user can use the machine learning tool to automate the task, but also use the web tool to correct it. So this is more like when a machine working with human, we want to be able to improve the overall result. Because typically if you say a machine learning model gives you 90% accuracy, is it useful? We don't really know. Maybe it's not very useful, you have to be 99% accurate, or maybe it can be useful if you only have 50% accuracy. So this is what we want to work on. We work with historians a lot. What I learned is people often say that history repeat, and they do repeat. So one interesting project we work on is to look at really old historical maps and how those maps were when Venetians, they send people out to the world and to record information back, and then they put it on a map to help them understand the culture and importance of different parts of the world. So that's very interesting. You get to see the entire world from their eyes. You will be able to know, okay, so this city has a very heavy trade with the Venetians, that they use a special symbol to record that city, right? But still, map in that sense, it's a visual tool to help communication. But to understand more about the history, what we can do as a computer science to help is we can extract the information and help connect those information to all other existing knowledge that we have known for that area or from that time. One way to help us forecast for the future is to understand the present and the past. In the past, to do that, we have historical maps. We have lots of them, cover a large area. The really technical difficulty is how do we use information in the historical map in a very efficient way to help us understand current situation and forecast for the future. So we are training AI machine learning models to read maps automatically so that we are able to get all this information created by professional cartographers in the last 125 years so that this information will not only live on paper and disappear. If this map disappears or if we cannot find them, we will not have the knowledge to help us understand the current world and also forecast for the future. For example, if we see wetland is shrinking in some area, or forestry is shrinking in some area. And we also know maybe in the last 50 years, there was a new policy, right? So how do we use this knowledge of forest areas or wetland areas and then the policy that was instituted 50 years ago to help us understand was that policy useful? How does it change the areas of the wetlands in the entire U.S.? How does it change shrinking of forest areas in the entire U.S. as well? ISI means a lot to me. ISI changed my career. When I started, I didn't even think I would work in academia. I want to get my PhD for sure, but I don't have any interest in working with students. But ISI actually changed my perspective on that. Graduate students, master students, PhD students, senior researchers, everybody can work together to solve important problems, and it's really fun, and I enjoyed it a lot. I stayed in academia because of my experience at ISI.